A very good afternoon to one and all. Let's begin today's session with a silent prayer. Hello everyone, I am Professor Jocelyn Jose, Department of Physics in Joseph College, Bengaluru. I welcome you all to today's webinar on renewed interest in Venus, our nearest planet. Venus, the hottest planet in the solar system, often called the Earth's twin sister because it is nearly equal in size and mass. Though it takes hardly 100 days to reach Venus, we don't find much concrete expeditions to Venus for the past 30 years. But today, we find a renewed interest in Venus with the Indian mission plans to Venus, the Shukrayan-1. We have here today with us our guest speaker, Professor P. Sreekumar, the Satish Dhawan Professor ISRO, Indian Space Research Organization, the pride of our country, to enlighten us on our topic, renewed interest in Venus, our nearest planet. On behalf of our principal, Reverend Dr. Victor Lobo, SJ, and the head of the Department of Physics, Dr. Maria Sahayaraj, I extend a warm welcome to Professor P. Sreekumar. Here is a brief profile of Professor P. Sreekumar.
His PhD in physics from University of New Hampshire, Durham, US, after completing his MSc in physics from IIT Mumbai. After 10 years as a research scientist at NASA's Goddard Space Flight Center, Professor Sreekumar has been head Space Astronomy and Instrumentation Division from June 1999 to December 2009 and Group Director Space Astronomy Group from 2010 to 2013 at ISRO Satellite Center, Bengaluru. Since 2013, he has held the position of Director, Indian Institute of Astrophysics, Bengaluru. His research interests include high-energy astrophysics, extragalactic gamma-ray background, X-ray studies of Sun and the solar system, astronomical instrumentation and X-ray optics. Professor P. Sreekumar has more than 120 publications in refereed journals, and apart from this, he has also received various outstanding awards like Chandrayaan First Payload Team Award in 2009 and NASA Group Achievement Award in 1991.
Dear friends, we are very fortunate to have a very distinguished scientist to enlighten us on today's topic. Let us be alert, and I request all of you to mute your microphone and to turn off your videos. You can raise your questions in the chat box regarding the topic. Now I request Professor Sreekumar to take over the session.
Thank you, Professor Jocelyn, and thank you to St. Joseph College for this interesting process of actually bringing all our students together for discussions that are otherwise difficult in the current conditions. So today, my goal would be to give you a glimpse of why Venus as a planet is interesting for a visit from India as well as from other countries. We are at the very early phase of such a program, and I am also only learning elements of this, so bear with me as I go along. So to begin with, let's take a look at our solar system, which we have for many years assumed is the only solar system that we know of. Of the 8 planets out there, the inner 4, Mercury, Venus, Earth, and Mars, are rocky planets, and they are much closer to you amongst each other, and we have initiated, as humans, we've initiated exploration programs that lead to our nearest satellite, the Moon, to Mars, and in the past, Venus as well. And there have been some limited missions from NASA and from the European Space Agency going to the outer gas giants that you see out there. Today, this solar system, which has always been partially understood with regard to its origin and evolution, we now also are looking at systems way beyond our solar system. About 25 years ago, when the first set of astronomy observations suggested the presence of planets around other stars, the concept of exoplanets, the field emerged, and there was a lot of effort to look for such exoplanets among orbiting other stars in our galaxy. And this has actually led to major missions like Kepler, which has actually discovered more than a few thousands of such orbiting exoplanets. And what I show here is one of those systems called TRAPPIST-1, which actually shows a series of satellites, a series of planets around this dim star compared to our sun. But that really shows the presence of such solar systems out there. And one of the fundamental questions we would really like to really address in the long run is to ask, can some of these planets be Earth-like? Could it be habitable? And could there be life on such planets? And that's an incredibly important question for all of humanity. And so this is a very fast emerging field of research. And there is some link between this and what we talk about Venus today. So TRAPPIST-1 is only 40 light years away, which is really a stone's throw compared to astronomical distances that we talk about. And so it's very important that we take a look at it in the context of our solar system. Interestingly, the second planet here, TRAPPIST-B, 1b, was actually also observed using the discovery involves the Himalayan Chandra telescope, the 2-meter telescope that the Institute of Astrophysics supports at Hanley at 4.5 kilometers above sea level, and that is actually be able to the scientists were able to use that to really look at the transit light curve. In other words, how the light from the star was actually dimming in the present planet going in front of it. So we have a role in this TRAPPIST-1 as well. Now, the exploration of our solar system has been over the decades largely driven by ground-based studies. We use telescopes right from Galileo onwards. We then have, with the space era emerging in the 50s, we have had flyby missions where a spacecraft will not orbit it, but just zip by the planet, study it rapidly during that short time it has to study the planet. And subsequently, while we understood better the gravitational potential of these planets, we are able to orbit these planets. And these have actually happened both from Moon to Mars to Venus, Jupiter, many others, Saturn, and so on. We've also used balloons in some systems where there's atmospheres, where balloons can be used for slow measured observations of the atmospheric phenomena. In some cases, landers are done. Landing is a challenging issue, soft landing with all the equipment, safely ensuring everything works, and then the ability to really transmit all the data back to Earth is an incredible challenge. But humans have succeeded in this effort as well. Recent focus, of course, has been the Moon, with it culminating very soon in this new interest in actually humans going to the south pole of the Moon, with NASA leading an effort for the 2024 timeframe. Mars has also been a planet with substantial interest, and there have been many missions to Mars, and there's a current mission being planned to be launched on the 30th of this month, March 2020, that actually where NASA hopes to really start looking at bringing back some samples from Mars, which can actually tell you a lot about the planet and its history and evolution. If you look at Venus, let's just look at some simple facts. As Professor Jocelyn said, this is very similar in size to Earth. It's closer to the Sun. So the Earth is at a distance that we term as astronomical unit. Earth is 1 AU from the Sun. So in comparison to that 1 AU, Venus is at 0.7 AU. However, this means much greater influx of solar energy. Roughly 2 times the solar energy input comes in to the top of atmosphere of Venus compared to that of Earth. Venus has a high albedo. It does reflect a large fraction of the sunlight that falls onto it because of the clouds, and hence the absorbed solar energy of Venus is actually less than what it is by Earth, and we will come to this discussion a little later. Venus rotates slowly, we don't fully understand it, and in retrograde, it actually rotates opposite direction to how Earth is and other planets are rotating. It has an unusual day, which is 243 Earth days, which is longer than a Venus year, it is 225 Earth days. The sun rises every 117 days, and it moves from west to east. And given Venus day, there will be 2 sunrises. Now, I think that confuses everybody when you have 2 sunrises on a given day. It's hotter than Mercury, even though Mercury is much closer to the sun. Its surface temperature is of the order of 460 degrees or higher. And these temperatures, many metals will melt. Its pressure is about 100 times the pressure on Earth, roughly the pressure you'd feel if you go down a kilometer in the water in the ocean. And it's thick clouds, and these thick clouds are not made of water vapor, but sulfuric acid. At least we believe so. So clearly Venus is not an ordinary planet. It looks completely out of control with regard to, if you believe that Earth and Venus initially started in a very similar environment with similar initial starting conditions. If you look at a global view for Venus as this,
Sir, we can't hear you. We can't hear you. We can only see that global view presentation. The audio is stopped.
till that time, hear me?
Yeah.
Are you able to hear?
Now I can hear. This is slide 5, global view.
Slide
Now
5. Are you able to hear?
Yeah. Now
Is the audio okay now?
Yeah. Now audio is okay.
Okay.
And we see that global view. That's
I'm holding the mic. This is okay. I'll just. So in slide 5, what we see is a picture in ultraviolet, and this ultraviolet image actually shows it's not completely uniform. What you see is some structure, and the structure could arise from the fact that the reflecting material is not uniformly spread, or there could also be what are called absorbers of ultraviolet. There is a mysterious UV absorber that we still do not understand as to what it is in the Venus atmosphere. But this is how the global view looks like in ultraviolet, but it's not telling you much about the surface of the planet. If you want to look at the surface and below the surface, we then need to use something else, and that is we have to use radio waves. Radio waves can penetrate the cloud, and if the wavelengths are longer wavelengths, you can actually penetrate the surface as well. So radars act as cameras for a Venus mission, and we use the radar to derive topography, the shape of the surface, structures on the surface, to look for craters and flows and other things. When you do these radar imaging, this is typically done using what is called synthetic aperture radar. Synthetic aperture radar is like a regular radar that you have in an airport. The only difference is the radar is on a rapidly moving platform, the satellite, and hence by the time the reflected radar signal comes back to the satellite has moved, the radar has moved quite a bit, and hence it acts like a large aperture radar. Hence it's called synthetic aperture radar. So when you do this synthetic aperture radar from multi-angles, you can actually create stereo imaging, and from the stereo imaging you can create what are called digital elevation models, which gives you a measure of the vertical structure of the surface of the planet as well. And these digital elevation models are absolutely critical when you want to study areas of, if you want to study volcanism on the surface, compositional studies, and I'll tell you how that comes in, and something on age. If you recall, on the moon, for example, we study age of a surface by looking at the crater density, size distribution, crater size distribution. The older ones will have many more craters, and so there is a connection to this. But however, on Venus, this is a bit more complicated because we believe there's volcanism that is constantly reshaping and resurfacing, which is hiding the earlier craters. There is, of course, other problem that with such a dense atmosphere as what we have on Venus, impacting material often gets destroyed in the atmosphere of Venus, and so you don't see large number of on Venus. Now, to look at the surface, there are also narrow windows in infrared, close to about 1 micron, 1.1 to 2 microns, where the atmosphere is transparent to infrared radiation. And we can, if you have instruments that can make images or derive the emitter radiance through these narrow wavelength ranges, we can use that to really look at the surface. And the emissivity, which is really a measure of the distribution, spectral distribution of how a given substance radiates at a given temperature, that emissivity is characteristic of rock types. So if I can map out the emissivity at different wavelength bands, I can use that to really derive the surface composition using remote sensing techniques. Now, the place where radar data comes in to address composition is this emissivity is very strongly sensitive to topography. If I don't have topographic information, I would find that the emissivity is very different and incorrectly assessed. So we use the radar data to correct the observed infrared emission and then derive emissivity from it to derive composition of rocks. Here is an image from the Magellan, Magellan was a very major mission that NASA flew in the 90s that actually carried a radar, and it produced a surface. Nearly 98% of the Venus was actually covered with about a resolution of about something close to about 100 meters. And what you see are mountains, flows, and here is another detailed close-up map of Mat Mons, which is a volcano, about 8 kilometers, and you see lava domes, outflows of lava, and this lava is what is leading to a lot of resurfacing. So about 80% of the surface of Venus appears to be young as 500 million years. I mean, that's young for a planet. Unlike other bodies like the moon, where you really see things as old as 4.2, 4.3 billion years old. So what is causing this resurfacing? We believe it's volcanoes, but we really need to have direct evidence of these as we continue these studies. And this shows a global map of Venus. The darker regions are higher altitude, higher locations, which are often called as terra. And on the top right, you will see Maxwell Mountains, the tallest mountain on Venus, about 11 kilometers, still much smaller than Olympus Mons on Mars, which is about 22 kilometers. And you have, so there are the two big, large upwellings is in Ishtar Terra and Aphrodite Terra. And then you will see all these structures that you can see, if you look carefully at this map, suggestive of this large amount of volcanic evolution. It appears even on Venus, we need to worry about the corona. You see there is an area called Artemis Corona, named after, for of course, obvious different reasons. On the issue of volcanism, the European Space Agency mission called Venus Express was able to actually map the thermal enhancement at the peak of some of these mountains. And what you see is the suggestion of the fact that there has been volcanic activities, could be recent, and that is an important question for every future mission to really look into. Now let's come to the atmosphere of Venus. It is heavily dominated by carbon dioxide, 96.5%. Then there's the next dominant species is nitrogen. And then you have very small amounts of sulfur dioxide, argon, water vapor, 20 parts per million, and so on. It's a thick atmosphere such that below this cloud layer, only about 10% of the solar radiation reaches the surface. So the first set of Venus landers actually carried a flashlight with them to take pictures, thinking that they will be very, very dark, but it wasn't so dark as was initially envisaged. The temperature, surface temperature, as I mentioned earlier, is close to 460, 470 degrees centigrade, and as you go higher up in altitude, it decreases. And there were studies that were done using the Pioneer Venus Orbiter mission that actually showed from polarization measurements and certain other studies that the refractive index of the cloud layer was roughly at 1.34 or so. And one way to explain that is to really assume that these clouds are made up of sulfur, H2SO4, sulfuric acid droplets forming the clouds. And hence the sulfur cycle is an important part of understanding Venus atmosphere and dynamics in the atmosphere. So there is this suggestive indication that these clouds are made of sulfuric acid. Below the clouds, the winds are always fairly low, whereas as you go into the clouds, this wind picks up to such an intense level. What is shown here in this plot is, it goes up to about 100 meters per second. That's pretty strong winds. At 55 kilometers where these clouds are, the pressure also decreases. Pressure is pretty close to what we are used to. And the temperature is also very close to what we're used to, around 27 degrees. Sounds like a good place to actually have life survive. And we'll come to this discussion at the end of the talk. Now, very recently, there's a mission that's going to Mercury called Messenger, which the United States actually, US had actually launched some time back. On its way, it actually had to fly by Venus and it used its instruments to study Venus. And when it studied Venus, what it found is, interestingly, even just in that flyby, they could actually show that the nitrogen content is much larger above the clouds compared to below the clouds. This is a completely new, unexpected finding, and we still do not understand what is supplying this nitrogen above the clouds that makes it, about 1.5 times what you see below the clouds. So there is a fair number of elements in the Venus atmosphere that continues to remain mysterious, and that has to be addressed by future missions. When we study the atmosphere, we're primarily looking at chemistry. We look at the neutral component, we look at the ionized component. And the chemistry, what we have is often the incident photon from the sun interacts with the gas constituents, in this case CO2, and going through photodissociation processes. We could also have ionization process where CO2 gets ionized, and that ionized component can actually be part of other chain reactions. You could have cases where you exchange charge, oxygen plus exchanges charge with hydrogen, and then that goes off and continues in the form of other reactions. So all of this is actually driven by the incident solar radiation. Then you have neutrals, which show in the form of air glow, transitions of the molecules. Oxygen air glow is seen at night in the infrared, near infrared 1.27 micron, also seen in the visible band. Nitric oxide UV night glow is seen. Hydrogen, Lyman alpha night glow is actually also observed. There's been a desire to look for this oxygen green line and red line, which is seen in the Earth's atmosphere. There are some interesting pictures of oxygen green and red line taken from the International Space Station that are available on the internet, beautiful images. But we don't seem to see these evidences on Venus. There have been certain interesting observations from ground using the Keck telescope, but future missions certainly will have to address this in the context of why we don't see it, if it's only a question of observing these at the right time with the right solar phase angle, etc. There is also an ionized component in the Venus atmosphere. This ionosphere can be used to study plasma waves, which are suggestive of electrical processes sometimes. Electric discharges can lead to plasma waves. There is also a lot of electrons, and one of the key things would be to study the density, temperature, temporal and spatial variations of electrons and ions in this Venus atmosphere. As I mentioned earlier, the Earth's atmosphere, the Venus atmosphere shows these unusual high-speed winds at the cloud level. And there is a lot of convection in these places. There's a lot of solar heat input as well. The rising hot air moves The equator gets a lot of the lot of the thermal load, and it moves to the polar region, cools, and then forms a convective circulation. And but this north-south flow is much slower compared to the east-west flow, which is what is driving the superrotation. The planet itself is a slow rotator compared to Earth, the slowest rotator in the solar system, and hence its Coriolis forces are small compared to that on Earth, and which on Earth our winds are actually driven by Coriolis forces, but on Venus, we really, since the Coriolis force is very small, we really still need to understand exactly what is driving this very fast wind, which is at the rate of 100 meters per second. Atmosphere circulates around Venus, and in about 4 days, it actually completes a full planet. So it rotates 60 times faster than the planet. Those similar things are seen on Titan and Jupiter and Saturn, and Venus really shows the most extreme case of superrotation. And we don't seem to understand what is driving the superrotation. Just to give you a measure of these things, one of the fastest, this is the second fastest wind measured on Earth at 103 meters per second, at top of Mount Washington, New Hampshire. I was fortunate to spend a few weeks there doing some studies while I was a PhD student, and it's an extremely severe environment, and one can imagine at 100 meters per second wind on the cloud layer of Venus, how severe the environment would be to understand the dynamics that actually go on there. Sulfur dioxide is another trace gas, but still measurable, and in the Venus atmosphere. And there, people have been measuring this since the early days of the Venus exploration programs. On Earth, sulfur dioxide largely comes from volcanic activity. And sunlight actually dissociates SO2 in a few days. So on Venus' upper atmosphere, the SO2 would be destroyed and dissociated, but something is replenishing it. And what we see in the graph on the left is it shows that over time it seems to decrease, shows small increases in the 1990s, but then we didn't have measurements for a long time. And the Venus Express mission, the European Space Agency mission, was actually able to catch both the rising phase as well as the decay phase of the SO2. So we have nearly 40 years of data that shows the sulfur dioxide content on Venus is changing. And so the question is, what is replenishing the sulfur? Could it be volcanoes, as it happens on Earth? And that is an important question for the future. As in any atmosphere that has winds and ionization processes, etc., and convection, you expect to see lightning. And so there's been always an interest to look for lightning on Venus. Some of the good ways to look for lightning is in the radio or an optical. And there have been searches. Some of the early Soviet Venera landers reported the detection of very long frequency radio signals suggestive of presence of lightning. And there have also been plasma waves, Whistler waves, seen by the Pioneer Venus Orbiter mission. And radio bursts were seen by the Venus Express mission recently. The visible component in the form of optical flash at 777.4 nanometers, an important line energy at which we see it on Earth, has been the focus of study for many years. But as of now, we don't seem to have good evidence to see in the optical for the presence of lightning. There have been other flyby missions that have tried to study this VLF radio signal, like Cassini, but could not see it. And so there is this constant concern, is lightning really there? And today, if I were to make a conclusion, I would say convincing evidence for lightning is still escaping us. Although there is clearly good reasons to believe there's electrical discharge phenomena happening in the clouds of Venus. The Japanese mission, Akatsuki, which is currently in orbit around Venus, continues to search in optical at the 777.4 nanometers, but its most recent reports also suggest non-detection. But it could also be because it has not been able to spend a lot of time close to Venus, given its unusual orbit. Here is Akatsuki orbit around Venus, so only it is getting very, very close to Venus. are these measurements, are these studies possible? As some of you may know, that Akatsuki was this mission that Japan launched in 2010 to Venus, but in its initial attempt to enter the Venus orbit, it did not succeed. However, the spacecraft was then left in a heliocentric orbit, and then it waited 5 years. In 2015, it once again found a way to get into the Venus orbit. Brilliant work by the Japanese team. And today, Akatsuki is around Venus looking for this signature for lightning. As always, one is interested in looking for water on Venus, and water on Mars is an important study for us. Water on Earth is so critical. Everything we know of life is really linked to water. So water on Venus is an important question. And there's always this worry that was there water, and then did that simply escape? Atmosphere of Venus, as in all other planets, including Earth, evolves over geological timescales. And that's important to understand. There is also input of energy from the sun, both in terms of ultraviolet and X-rays. And this energy and momentum transfer from the solar wind, this steady flow of electrons and protons from the sun, is also impinging on Venus. And Venus doesn't have an intrinsic magnetic field, so the solar wind directly falls onto the surface of Venus. All of this will have a role in actually changing the atmosphere of Venus. One way we often look at escape of water is to look at this ratio of isotopes of hydrogen, deuterium over hydrogen, often called the D/H ratio. And if you look at the D/H ratio, you can measure it. And what we see is this suggests there is a higher escape rate for the lighter hydrogen. The assumption, of course, is that deuterium is constant. Deuterium is from the original for solar nebula formation, and so there is no additional deuterium being synthesized anywhere. And hydrogen, so that there is a change in D/H ratio, is only because of hydrogen is changing. And so this seems to suggest that there's been a high escape rate for lighter hydrogen compared to deuterium, and hence that could suggest loss of water as well. The study of this older, if you recall, I mentioned the fact that the constant regular volcanism activities on Venus leads to resurfacing of much of Venus. However, the highlands, the higher locations in the tessera could actually be good places to look for the oldest rocks on Venus. And these oldest rocks could actually tell us something more about the early presence of water, a key and important information that we need to know about Venus. There are proposals right now in the works in the US and elsewhere where they're talking about actually landing missions on this tessera, which is, of course, a very challenging thing. It's landing on a flat surface is challenging. On a mountainous terrain is even more a bigger challenge. But this that sort of sampling could actually tell us something more about the presence of water on Venus. But clearly there seems to be growing evidence of the fact that there was a time when Venus was had a lot of water and much of it escaped. And the solar wind interaction with the Venus atmosphere is a key to understanding how other planets may also survive, how water on other planets could survive evolutionary processes, and hence Venus has an important role to tell us with regard to habitability in exoplanets. We've often heard that there is a runaway greenhouse effect on Venus. Venus, as was mentioned earlier, is extremely hot, hotter than Mercury, even though it's further away. So let us look at the key parameters that determine the temperature, surface temperature of a planet. I've listed just these four: distance to the sun. Earth is at 1 AU, Venus is at 0.7 AU. Albedo, which is a reflection, the amount of light that is reflected back. Earth has 0.3. Again, we have clouds that can give rise to reflections of the solar light. Venus, because the cloud layer is thick, is 0.7. So only 30% of the solar energy is actually absorbed by Venus, where in comparison 70% by Earth. And then finally you have to ask what is the efficiency to retain heat, and we find that Venus has a higher efficiency to retain heat, and hence the temperature rises. Now on the little box on the right side, I put in some typical numbers. If I assume 100 units of solar energy is incident on Earth, then that would then mean, given the distance to Venus would have 193 units. But if I now put in my 70% absorption at Earth, that comes to 70, whereas a 30% absorption of Venus makes it 53. So actually, the 53 is a smaller number. Venus should have been colder than Earth. Surface of Venus should be colder than Earth. However, we know it's not true, and says the surface temperature of the planet has more to do with the atmosphere than proximity to Sun. In the plot below on the right side, you see how rapidly the solar flux actually decreases. And so that alone is not enough. We really need to worry about the atmosphere as well. In this atmosphere, as I mentioned earlier, carbon dioxide is the most important gas. And then you have sulfuric acid clouds. These droplets can scatter radiation back to surface. It'll heat the surface again. And as more water vapor enters the atmosphere, which is an efficient greenhouse gas, the system retains more heat and the runaway greenhouse effect takes hold. Now, once much of this water has escaped, then the CO2 is no longer has a sink, and the planet just remains hot. So with the loss of water, we believe planet Venus has reached this kind of baked condition. Now, not everybody believes this is necessarily the whole story, and some of the future exploratory programs is to really look for other ways in which Venus has reached this high temperature. But today, this is one possible way in which we can understand the high temperature on the surface of Venus. Now, if you want to go to a mission, have a mission to Venus, Venus is of course closer than Mars to Earth, and you have to look for launch opportunities, because you don't want to use the minimum rocket fuel to actually get there. And on the right hand side is a plot that shows in blue is the orbit of Earth, and in red is the orbit that Venus Express took. As it got launched from at this point, it took time and caught up with Venus, which is in the inner circle. So it caught up with Venus out here. So this opportunity of proximity to Earth comes every 19 months. For Mars, it's every 26 months. So every 19 months, we have a window of opportunity to actually send a mission to Venus. So I just put down on a possible launch date for a mission, 5th of June 2023, when things are close to. So here is Venus at that time, Earth is here, Mercury is out here, and Mars is, way out here. And then about 3 months later, it arrives, October 12th, and Venus is up here, has gone past Earth. Venus moves faster than Earth. And meanwhile, the spacecraft would have actually reached Venus. And this is the time scale we're looking at 2023. And that's one way to really go to Venus. Now, similar launch opportunities and similar configurations are available in the 25 timeframe, the 26 timeframe, and so on. 2031 is an important timeframe that many space agencies are looking at to launch large missions when the energy requirement is one of the lowest. But look at the global plans for Venus exploration. Until now, we've had series of missions. As I mentioned, Venus wasn't actually ignored. Even in 1961, very, very early in the space age, there was the Soviets had Venera 1 head off to Venus. The successful one flyby was with Mariner 2, then Mariner 5, Mariner 10, Pioneer Venus Orbiter, Magellan, Venus Express Akatsuki, and a long list of Venera missions, about which I'll discuss a little later. And now Akatsuki is available going around Venus. Looking into the future, we are thinking about a mission from India. US has 2 or 3 proposals out there. There's maybe partly with Russia or independently. Russia has a Venera D mission that they have been working for many years. It was because of the Soviet Union breakup that didn't go through. Otherwise, that would have been an earlier mission. And Europe certainly has a mission called Envision that they are planning for the 2031 timeframe. And to have a slide on India's plans for Venus exploration, we're looking at an orbiter mission that would place a spacecraft in a 200 by 600 kilometer orbit Now, as it enters the Venus, initial parking orbit is very large. It's 500 kilometers or 60,000 kilometers. But because Venus has an atmosphere that extends out, it uses aerobraking to really bring it to the closer science orbit, from where you can actually make some measurements. And we're doing it at 90-degree orbit, so you can think about, so there's in the vertical plane, this orbit is there, and the space and the planet rotates under that, and this is optimized for mapping studies. And as one could imagine, it has a series of science objectives, which includes mapping the surface at higher spatial resolution using a synthetic aperture radar. We plan to really, we have actually successfully shown that we can fly synthetic aperture radars and planetary missions like Chandrayaan-2, which today produce some amazing images of the moon at multi-frequencies and using polarimetric measurements. And that is the kind of data we are trying to derive from Venus at resolutions that are about 3 times better than what was done by Magellan. And this would be used to identify surface and subsurface features, including volcanic hotspots, determine structure and composition of the atmosphere, understand clouds and lightning on Venus, and address superrotation, investigate the ionosphere, solar wind-induced processes, and so on. Now, if you look in all of this, what I mentioned, unlike other planets, we don't have a lot of data from the ground. We haven't had many surface probes, but there have been, and that has been the most incredible thing as I look at it, is landers on Venus. So the Soviets had a series of landers. Venera 7, look at the date, August 1970. 1970, this is, 50, Sputnik was in 57. And it survived for 23 minutes on the surface of Venus. Venera 8, 1972, just 2 years later, landed, sent back data for 63 minutes. Venera 9, June 1975. It had 2 cameras, and the lens cap didn't come off, and so it got partial images. Venera 10 landed just 3 days after 9. I don't know how they managed to have so many missions. Again, same problem, lens cap issue. Survived for 65 minutes. Venera 11 and 12 again had lens cap issue, but in 78. Venera 13, October 81, and it survived for an incredible 127 minutes. And Venera 14 in 81, survived 57 minutes. And finally, as part of a Halley's Comet mission, the Soviets had, on the way to Halley's Comet, they actually deployed 2 balloons, Vega balloons, into the atmosphere of Venus, which also had 2 landers also. But the balloons actually survived and floated at 53 kilometers for about 60 hours. I mean, no one else has been successful in flying balloons on Venus. We would really like to have a balloon in our mission to Venus, but it has a lot of technical challenges in enabling it. So if you look at this image that came from Venus, Venera 13, here is the left camera, your right camera, and then they put it together into a combined view. Pretty amazing, and so many years ago. And we have someone who's actually managed to take this panoramic view and actually make it look like what would the scene look like if we were standing on the surface of Venus. And you can see very rocky and structured environment. Here's another image from another Venera 10. That landscape looks different, but it's truly amazing that we have some images from the surface of Venus. But it's very clear what is required for the future is many more such images and the ability to actually survive many days on the surface of Venus. And today there are many plans underway under which such things are being considered in the near future. So let me close with this last slide. Why are we having a revised attention to Venus? One, as I mentioned, there's a need to understand the runaway greenhouse effect. This could have some implication for Earth as well, as we're looking at the whole concept of global warming, and it would have some effect in addressing habitability of exoplanets that we would soon be confronting as new missions are out there identifying habitable planets and presenting to us. There is also this very incredible possibility of looking for biomolecules and life forms in the benign layers of the atmosphere of Venus. I mentioned to you around in that 50 kilometer height, where the temperature is close to 25 degrees and the pressures are about an atmosphere or a little less. One could think about as a conducive environment for life forms to exist. In 1967, Morowitz and Sagan, yes, the same Carl Sagan, wrote this amazing paper about the possibility of life in the atmosphere, in the clouds of Venus. And there's a recent paper of Sanjay Limay, who summarizes, and many other references are there in the 2018 paper that talks about the possibility of such a thing. We would have been very happy if we could have enabled a mission that actually bring back a sample of this air atmosphere from the 50-kilometer cloud layer back to Earth for very detailed studies. It would really, we can let loose the incredible amount of tools we have today in our laboratories to really understand this. However, there are a lot of challenges in pursuing that. We also need to address the issue of water in the inner solar system. As I mentioned, there is a distinct possibility that there were three beautiful planets in our solar system in the past: Venus, Earth, and Mars. With water in these planets, and who knows what else. That would be a wonderful thing to know. I said sightseeing planet en route to Mars. There have been some recent studies that show that one of the best routes for humans to go to Mars, as you all know, NASA is seriously looking at a human mission to Mars, maybe when China is considering it. One of the possible routes is to actually take a route through Venus. You do a flyby Venus and then go to Mars. And that is interesting because it has, has many implications. It just keeps an astronaut busy. There will be months of idleness otherwise. As you get close to Venus, there could be observations, there could be it's a distraction at some level. But there is this possibility that a future route to Mars always goes through Venus. And certainly, we would like to understand Venus very well. And India certainly has been steadily contributing to this global exploration program with our Chandrayaan 1 and 2, Mars orbiter mission, Chandrayaan 3 next year, plans for Indo-Japanese mission for a South Pole landing mission on the moon, and hopefully a new mission to Mars as well. So it's in this context that Venus comes to us, and we've decided to organize this most likely in collaboration with many international partners who will be contributing some experiments to the planned mission, India's mission to Venus. Thank you, and I will answer any questions you might have.
Now I request Professor Veena or Professor Parul to raise questions from the chat box.
Parul, you can ask the questions if there is any.
Ma'am, there aren't any questions yet on the YouTube. So there is one in the chat box here on the in the Google Meet.
I can see that. I see that. Speaking of biomolecules, what is the scope of astrobiology research in India? Does ISRO have plans for microbiological exploration of our solar system? Yes, indeed. Astrobiology, in the context of all these things, yes, we do have to really take up astrobiology research. As you are aware, we do have this microgravity platforms emerging, and opportunities for microgravity research are emerging from the human space program, the Gaganyaan mission of ISRO. There are test flights prior to that, and there could be also future planetary landing missions, which will also require the need to search for organics and for biomolecules. So there is a discussion underway with colleagues at various academic institutions, ISRO, Pune, and many other institutions, under which we are trying to come up with a document, vision, or roadmap for astrobiology research in the country. So this is something that is being taken very seriously now.
Any more questions from the audience?
Sir, there is a question on YouTube. Ruby is asking, does the retrograde motion of Venus affect the Earth in any matter?
No, it does not. It does not. However, we would really like to, because they are, it doesn't affect it, but we would like to know what led to it. There are, of course, models that suggest that it was originally not in retrograde, but got during a massive collision, it could have been spun the other way or flipped, and that lead to this retrograde motion. But today, we don't fully understand it, and it doesn't have any direct implication on Earth.
Okay. There is another question, sir.
Yeah.
Will terraforming be possible at Venus as we envision it for Mars?
Well, terraforming on Mars, because you have a flat, you have a solid surface on which you can set up a bubble and change the breathing environment, the composition of the atmosphere you breathe in, control conditions which you can grow plants and so on. Venus surface, as you can see, with 92 bar pressure and these temperatures, you just cannot survive there. What we need to do is to only look at a floating platform on Venus. In principle, it is possible that if you have a floating platform at 50, 60 kilometers above the surface, you could have temperatures and pressures that are manageable, and you would then have to have a large enough bubble in which you can actually change the environment that is appropriate for terraforming. But that is a very expensive and technically difficult challenge, yes. But in principle, possible. Yeah.
Okay, the next question is from Kirti. Could terrestrial life be possible in Venus just like Mars?
Well, we don't know. It's possible in the sense, as I said, there is, as I just now mentioned, in the clouds of Venus, there is a sweet spot for pressure and temperature related issues. That still doesn't agree. It is still not suitable in terms of for human survival with regard to oxygen, etc. But CO2 exists, and there are many life forms that could survive in principle in that CO2 rich environment. So it is possible, and we really have to go out and actually look for it.
Thank you, sir. The next question is from Rajesh. He is asking, how come sulfuric acid ended up in the clouds of the Venus, and are there any water resources out there?
Well, we don't know the water resources, and that is one of the key questions we have to really address. But there is trace amount of water that we can see from spectroscopic signatures. So we know water is there at trace levels. So water, as I mentioned earlier, does play this important reaction in the atmosphere where the ionization and the photodissociation by the solar incident radiation gives rise to a cycle where oxygen, CO2, gets broken and produces atomic oxygen, which is a very reactive form of oxygen, which then participates in various other forms under which the SO2 component is also translated into H2SO4. So now, beyond that, since we haven't really measured it in great detail, we do not know, for example, what else is there in those clouds. So until we have such data, right now the viability of thinking of sulfuric acid clouds, explaining the refractive index that we see, explaining the reflectivity that we see in terms of albedo, etc., appears to be consistent. But there's much more to do with regard to going there and looking for what exactly is in the sulfuric acid clouds. Water resources outside what we now know with regard to the atmosphere in terms of subsurface, etc., that sort of study has not been done. In principle, you can have a synthetic aperture radar operating at very low frequencies at a few hundred megahertz. that can actually go down to very low, deeper into the surface, to look for possibilities of water resources below the surface, but no such study has actually been carried out.
There is a question from Pavit. Can you go a little in depth about the 2 sunrises in a single day on Venus?
Yeah, because you have to think, as we said, it's a little confusing to us for us to think when the day is longer than the year. And so the sun is actually moving over. And by the time Venus rotates once, which is what we call a day, it has already moved more than once around the sun. So that's why we end up having these additional sunrises. I hope that makes sense.
There is another question. Sir, will ISRO plan for a land rover on the surface of Venus?
See, landing itself is a challenge, and then rover is the next challenge. Just to give you an idea, what is the challenge of landing? There have been missions like the Pioneer Venus Orbiter that tried to, or maybe it was a Soviet Venera, that the early ones, the pressures are so intense, our nominal material with which we make spacecrafts and experiments just won't survive. Electronics that is based on silicon that we currently know of will all melt and we'll be in bad shape. I mean, by the time you get down to even 40 kilometers. So what is being envisaged for future missions is where you may have to have two kinds of electronics. You may have something that works above the clouds, and the temperatures are not so severe, pressures are not so severe, and a completely new set of electronic instrumentation that works below the clouds, which is often using specialized technology. This could be like silicon carbide technology. So there you make your electronics out of silicon carbide, which is extremely tough. And then you have to really master it. So it is possible, people have demonstrated it, and now we have some ways to go to really get to that issue. Roving is once we learn to land and survive for a day, many days, and clearly roving becomes an important component of that, yes. But in the near term, we are not really looking at it. There's enough challenges to orbit and maybe even have a floating device in the atmosphere with the balloon type material would be a platform, would be a useful exercise for ISRO to take up at this stage. Yeah.
One more question is there. What are the implications of Venus not having a magnetic field?
Now, the magnetic field of Earth, for example, protects us from the solar wind and extreme ejection of particles during coronal mass ejections and during a solar flare. Now, because it channels it sort of pushes it away, and we are actually protected from these intense charged particles. On Venus, since that is not there, it actually hits the surface directly. One of the side effects of that would be that it could boil away the atmosphere of Venus. And that's an important question for us to learn and understand, because this also is an implication for exoplanet life elsewhere, because if the star that is hosting the exoplanet has a very strong wind, it could in principle ablate much of the atmosphere. So solar wind Venus without a magnetic field could lose a lot more of its atmosphere than otherwise.
I have a
yes,
question, sir. One second. If I heard you right, you said a day on Venus is much longer than a year. Is it?
Correct. Yes.
What is the reason for the slow movement on its axis?
Yeah, that slow movement we don't fully understand as of now. It is possible it wasn't born slow, it became slow. So the mystery is to really understand when and what made it go slow. But because of the slow movement today, as I mentioned earlier, by the time it spins once around its axis, it has already gone once around the sun and beyond that. And that's how it ends up being having this long day, longer than a year.
Is it anything to do with the magnetic field of Earth, which makes Earth go around faster?
No, not really. But there is a linkage with magnetic field and spin. When the spin is slow, then it's difficult to really create what is called a dynamo inside the surface of the planet. So the Earth's dynamo is sort of sustained by the fact that Earth is spinning at a fairly fast rate. So it's difficult to have a dynamo for Venus sustainable because of the slow spin. But that itself doesn't drive the presence or absence of, there's no direct, the absence of magnetic field is not the reason for it being slow. The reverse could be true.
Okay, thank you.
So a couple of them on YouTube are asking what kind of life is possible in carbon dioxide rich atmosphere of
So
Venus.
I am not an expert in this field. You'll have to really talk to an astrobiologist or any other biologist who can actually study, you see these superheated vents at the bottom of trenches in the ocean where at very high temperatures and with extreme environments, molecular bacteria and other life forms survive. So I really do not know. Sorry about that.
Okay, one more question. Okay, go ahead, Parul.
There's a guy, the question is not very clear, but I'll read it out to you. The movement of matter in space-time loses its energy by producing gravitational waves. If so, at what rate at which the Venus orbits decay predicted by general relativity?
I haven't done that calculation to give you an answer now. Yeah, so I'd really rather not comment on it at this stage, yes.
Right, sir. Many of them are thanking you on YouTube as well,
Okay,
sir.
no problem. Absolutely not a problem.
Okay, there is another question. Can we go ahead, sir?
Yes.
Yeah. Is the slow spin due to no presence of any satellite around Venus?
Well, I don't think so, but I cannot be sure of that. As I said, we don't fully understand the slow spin of Venus at all. So Venus doesn't have any satellites, but that hasn't affected Mercury, for example. So we don't know. I believe not. Yeah.
And one more question: are there missions like Vega balloons from ISRO?
We have done some studies to include a balloon package. You have to wait and see if we manage to pull it off. But in the next year or so, I think there will be some conclusions on the possibility of such an inclusion of such a balloon in our future mission. Yes.
One more question. Referring to your statement on using longer wavelengths to study Venus beneath the surface, is it possible to study the tectonic activity, if any, in Venus? If yes, what are the possible challenges?
Okay, tectonic activity requires a lot of coverage that spreads across a lot of time. And so in other words, you need a multi-year mission where you can repeatedly map and look for changes in the surface phenomena, which could then be linked to what is happening in the subsurface using a long wavelength synthetic aperture radar system. There is mixed views on tectonics activity on Venus. We believe it's not there, but as we improve the radar resolutions, the ISRO mission is looking at something maybe closer to a 30-meter resolution radar. There are new ones in the works now elsewhere in the world looking at 10-meter resolutions and so on. So as we improve the resolution, it becomes a lot easier to really address this question. But as of now, we don't really have a conclusive statement on the presence of tectonics. But subsurface structure can actually be discerned using long wavelength radars. Okay,
one more. Given such unfavorable conditions, do you think there could be any sign of biota? I don't know. Be it any level of organization, be it at any level of organization at all, even if hidden deep under the surface, could there be signs of life? Is any space research organization capable of carrying out exercises for such studies yet?
I mean, the future missions would really look at the atmosphere to look for life forms and other regions of the atmosphere, beyond not just the clouds but other regions as well. The lander missions could look for evidence of life forms subsurface, but these are all very challenging given the surface temperatures, etc. But as I said, today, as scientists, we should not be surprised by the extreme conditions in which life can actually survive. So it's a question of what we put as a boundary limit at which we can say beyond which nothing would survive. And I would say at this point it's all unknown, and we just need to go out there and explore and search for it, and then establish its presence or absence.
I think this question is answered already, or do you want to add some more, sir? Could you explain why Venus is a slow rotator?
No, I think we've explained that enough. I don't know that. I don't have an answer to it. That's why.
Yeah. One more is there. If Venus can't support any sort of life forms, what makes it interesting to study, sir?
Well, we study things that don't have any life forms also. But as I mentioned, one of the key things is to ask, how does a planet that is sort of similar to Earth, that had a similar starting origin as Earth, evolve itself into this hellish condition that Venus is today? And this has implications as we look at both Earth in its long run, as well as looking at habitability of planets outside the solar system. In the proximity of other stars. So it's linked to asking this question of how do planets and its atmospheres evolve with time, and I think Venus can give a lot of information in that regard.
Okay, that's all about the questions, I think.
Thank you.
Yes, sir.
I request Professor Bariya Sahayaraj to give the vote of thanks.
Thank you is the best prayer that anyone could say. I say that one a lot. Thank you expresses extreme gratitude, humility, understanding. Here I would express that from the bottom of my heart on behalf of you all. Thank you, Lord. Professor P. Sreekumar is presently in Satish Dhawan Professor ISRO headquarters. Of course, he is the backbone of our webinar today, with whom we stood before everyone. Dr. P. Sreekumar is our strength of physics department. God chosen him as he is, are instrumental in we getting the 8-inch reflecting telescope in our college observatory. I take this opportunity to thank him on behalf of the management and physics department. We also express our gratitude towards his attitude, as he is the one who gave us opportunity to conduct certificate course almost more than a decade. Thank you, sir. It is the name Space and Rocket Dynamic course was conducted in and out by sir support. Once again, thank you, sir, for your wonderful presentation and having accepted humbly in short period of our request. We love you, sir. I also like to mention few of them who were supported on behalf of our management and department. Especially, I thank Professor Jocelyn Jose. Also, I extend on behalf of her, I extend my gratitude to Professor Bonu Jeffrey, Department of Computer Science of St. Joseph's College, for all the technical support shared with us. This is the time to express our gratitude and thanks with an appreciation from the rest of the colleagues to our Professor Jocelyn Jose and her beloved ones in the family for organizing, arranging, and conducting this show successfully. I also thank all my dear colleagues for helping and encouraging Jocelyn Jose to take this task without any problem. Thanks to one and all who took part in this webinar and shown your good attitude and gratitude. May God bless you all. Thank you, Lord. Good evening to everyone. Please fill up the feedback form attached with the link with your having been here. So please fill up your feedback. Thanks to one and all. God bless you all.
Thank you. Thank you,
Thank
Dr.
you.
Joshi.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you all. Hi, Srila. Hi, Radha.